All right, new chapter. So in this chapter, we'll be talking about alkenes and alkynes, which are we refer to as what we call unsaturated hydrocarbons. So, like the alkanes we just got through talking about, they are hydrocarbons, meaning made only of hydrogen and carbon. But they're unsaturated, which means in this case they have double and triple bonds, respectively. Alkenes, one or more double bonds; alkynes, one or more triple bonds. And that's where the unsaturation comes in. If you remember back to alkanes, we said saturated means they have as much hydrogen as they possibly could. When we talk about unsaturation or units of unsaturation, double and triple bonds, the idea is in order to create a double bond in a hydrocarbon, we've got to remove a couple of hydrogens. So they're not now saturated with hydrogen. Okay, so that's where that sort of verbiage comes from. Let's just do this real quick. Some of this is probably in the slides somewhere. In fact, I'm sure it is. But let's just put alkenes, contain one or more carbon-carbon double bonds. Okay. So the idea here is we've got this. Now, though the things that are attached, I want to make that a little nicer because I want to talk about geometry. The things that are attached there, they could be hydrogens or R groups. And so I don't know if I want to... Right. We'll just leave them blank for now. But let me just make this a little nicer. But one of the things I want to point out is that notice these carbons, right? If you think about their geometry, or again, we've recently reviewed our geometry. These are trigonal planar, which means that these bond angles and this bond angle and all the other ones around the carbons are actually 120 degrees. Now, it turns out they're a tiny bit, well, this one would be a little less. Let me get this really quickly. I don't know that we need to go into this, but this one would be a little bit less than 120. This one will be a little bit more than 120. Double bonds, there's more electron density there. They take up a little bit more room than single bonds, but let's not worry about that. Let's say all of the the bond angles here, as we've learned, for something that's trigonal planar, would be 120 degrees. Okay, so if we're thinking then about alkynes, again, just to kind of intro this. Alkynes contain one or more carbon-carbon triple bonds. Okay, now these are linear. Okay, well, I'll just put this and then we'll draw that down here. And again, I'll purposely not put anything attached to those carbons. They could be hydrogens, they could be R groups, they could in theory be other, R groups being alkyl groups, they could in theory be other atoms too. But the thing that all alkynes have in common, again, is that they have this linear portion, the triply bonded portion. Remember, think about Vesper theory here. This is linear, 180 degrees, right? So the idea here is that the carbons of an alkyne will always be, or I should say, they will be, we're considering them central atoms, and the things that are attached to them will always be attached in a linear fashion in this case, right? Okay. Okay. So again, a lot of times, we're introducing something new. We want to give, an example of just a real world, like a real life example. You don't need to know anything for the exam about terpenes, but what's interesting, these are really interesting compounds. If I draw the line angle, bond line or line angle form of what we call an isoprene unit, it really looks like this. And so what's really cool about lots of different organisms, plants and animals, can do, not all of them, but many of them can actually take these isoprene units, and some of these isoprene units, this is actually isoprene. So if we think about isoprene, this is isoprene. Like this, sorry. This is actually isoprene, but you'll notice that in some cases these isoprene units have double bonds, one or sometimes multiple double bonds. So the general form of an isoprene unit is this. But what's kind of cool is, again, living organisms can actually kind of link these together. So these terpenes are created via what we call biosynthesis. There are enzymes that mediate these processes. We're not going to go into those details, but it's a really cool example of a situation where you end up with, and many of them, not all of them. In fact, you look at menthol there, that is not ultimately an alkene. I guarantee, though, it was made from an isoprene unit that did have an alkene functional group in it. And then the end result of some of these terpenes is that you also have double bonds in them. And let me just do this, just to kind of point this out. If we get just a different color here, if you're always those isoprene units again are always 5 carbon units arranged in kind of that way that we showed. Okay, so one of the things we do often when we're talking about, when we classify, whoops, that's not what I want to do, when we are looking for terpenes, is we will actually look for those, again, those isoprene fragments, and see how many there are. And so it actually helps us even classify terpenes as having a certain amount of isoprene units, and there you see those two, and they're linked together actually via those colored, like red or green bonds in this case. But a lot of these are really interesting compounds. A lot of them are have characteristic smells, and they're certainly used for colognes and perfumes and lots of other fragrance applications. So just really interesting compounds. So okay, back to kind of the stuff we need to latch on to here. Specifics related to alkenes and alkynes. It looks like we've already discussed those things. So alkenes, actually all this stuff, we just got through talking about. So next thing, get the pointer here. If you'll remember, maybe I'll do this real quick. We're not going to write everything out again, but I'll just put recall. I still have purple there. Go back to black. I'll just put recall. This is in our last chapter, right? We were talking about isomerism, and we were like, okay, isomers, right? And we've done this a number of times now. Structural or constitutional, right? We've talked about these. And then the other possibility are stereoisomers, right? And I'm just going to abbreviate some of these. And then we had conformational stereoisomers, which are subtype, right? And then we had cis-trans. Now, if you'll go back and if you'll go back and look at the definition, it was something like this. I'm going to try to just recall it for us in context. We said it was something like the cis-trans isomers differ from one another because of restricted rotation in a ring system or around the carbons of a double bond. So the ring system, right, we've seen before. In fact, I'm just gonna, do I have a, yeah, okay. So here's what I want to do. I want to just, again, recall, right? The last example, I think we were looking at like dye-substituted, this occurs in dye-substituted ring systems. In this case we were looking at dye-substituted. Let me just go back to hexane, right? And it was like 1,2-dimethyl cyclohexane or 1,3, or it doesn't really matter where the substituents are. But let's pretend we've got, this is a Hayworth projection. Remember we talked about it last time. We have 2 methyl groups and they're on adjacent carbons. Now, we know that we've got all these 2, but let's forget about all the hydrogens and let's just focus on the CH3s, right? So we can have 2 CH3s that are here and here, again, on adjacent carbons. We're calling this 1,2-dimethyl cyclohexane. I'll just put that, recall 1,2-dimethyl cyclohexane. Okay, so again, the carbons are on adjacent, the methyl groups are on adjacent carbons versus this situation, right? Where those CH3 groups, while they are still on adjacent carbons, and what I meant to say just a second ago is they are not only on adjacent groups. The one on the left here, I keep misspeaking. Let me slow down. They are not only on adjacent carbons, but they are on the same side of the ring, right? So these CH3s could have been above the plane of the ring as well, but they are designated, or this arrangement is designated as a cis arrangement of CH3 groups because, I keep talking, I can't write here, they are on the same side of the plane of the ring. Okay. By contrast, right, we got, if those CH3 groups, one of them is below and the other one is above, and again, it could be, let me get my pointer, it could be that this methyl was above and this methyl was below. Same idea, because if we flip this over, we get the same thing. But this, again, is what we refer to, we learned this last time, as a trans or a cross, right, arrangement. Okay, so cis versus trans in ring systems. Okay, let's say this though, cis and trans are also, and we wrote this into that definition, which is why we're not rewriting the definition, right, encountered with disubstituted alkenes. So not just disubstituted ring systems, but disubstituted alkenes. Now you may be thinking to yourself, well, what if we have trisubstituted alkenes, meaning 3 R groups, right, or 4 R groups? Well, it turns out there are multiple possible isomers in those situations as well, but we have to learn something new called EZ isomerism, or how to designate EZ isomerism when we're talking about tri and tetrasubstituted alkenes, and we just don't really go into that. If you're absolutely loving this, you're like, I gotta get more of this. We go into that in the year-long course, but let's kind of keep it as simple as we can here. So if we have an alkene, right, the double, like we said, a double bond, and we had, I'm going to try to make this look like our Haworth projection 1,2-dimethyl cyclohexane above, and I'm going to put the CH3s here and here. Now it doesn't really, again, matter. Well, let's just put hydrogens up here and here. Okay. So as we'll see in a second, this is called 2-butene. Okay. But don't worry about that yet. But the other, I'm just going to put or this just so we're clear here, right? All I would have to do is flip the molecule over to make it look like this. So these are the same. There's nothing, I'll just put these are the same. Okay. But I'll just put versus the situation where, again, we have the CH3 over here and a CH3 over here. And of course, we've got the hydrogens as well here and here. So this then is, and again, you can redraw this, or I don't know, I guess we can. Same idea. H. So same thing here. Right, and these are across. Now I guess I haven't even said that. Let me get my pointer. Now, again, we're thinking about up here the ring system as being flat or planar. In the same way, I kind of think about this as existing, this double bond as existing in a plane. If you could draw a plane right through it, or picture one. And the idea here is that both of those methyls in both of these situations are on the same side of that plane, or on the same side of that double bond. Sometimes we call it a double bond, a pi bond, or a pi system rather. But let's not worry about that. So we're calling this, again, these are on the same side, right? So cis, right? The substituents are cis, or the double bond is cis rather. So same side. The CH3s, right? Okay, so by contrast over here, I have a trans, a cross situation. CH3s are, I could have written that better, but CH3s are across the double bond from one another, or across that plane from one another. Okay. Now the thing that's important about, there's a lot of things that are important about that. And some of them we encounter in this class, others we don't. But the first reason that's important is, again, there are multiple possible isomers with the same molecular formula, but that are actually different. And we'll get a feel for the fact that I think when we talk about physical properties, maybe we won't, but it is true that different cis-trans isomers actually have slightly different physical properties in many cases. And so it's important in a lot of different ways. The first, again, one of those ways is that we would actually need to name these different cis-trans isomers in different ways. So we actually have to put the word cis or trans out front, and it's usually italicized, although we don't have to necessarily do that when we're writing the name, but that's the idea. Now, before we get to that, well, actually, we'll probably encounter it pretty soon here, but let's just take a step back and say, okay, we're going to start to name alkenes, okay, using this IUPAC nomenclature, and of course we encounter a few additional rules here. Now you see those there, okay? I won't read them to you. Well, I guess there is. What's going on here? Oh yeah, I just have some transitions in this slide, so there are actually 4 examples there. Okay, so you can read through those little bullet points there, those additional rules. But the first one I want to point out, and it's there, is that you've got to look for the parent, right? Like we always do, and we'll continue to always do. But the parent for an alkene has to be a parent that actually contains the double bond. Okay, and that's important because if we have a branched compound, we could conceivably I want to make sure I have the video. I just sometimes am paranoid. I've told you this before. Okay, we're rolling. We could conceivably encounter a situation where we circled a parent that was just as long as another parent for a branch compound, and one contained the double bond, or all the double bonds, and one didn't. So if you've got a double bond, one or more in a molecule, your parent has to contain those double bonds, okay? And actually double bonds take precedence or have priority over alkyl groups when we're numbering or naming compounds. Now I want to show you this, what we call a functional group priority list. Now, you do not have to memorize this list. I'll give it to you. I usually attach it to exams, but we'll come back to it lots of times. And I want the thing I just said about double bonds having priority over alkyl groups, which are derived from alkanes, comes from this list. Okay, do you see how alkenes are higher on the list than alkanes? And this is a priority list, so it's like hierarchical, meaning the stuff at the top has a higher priority than the stuff on the bottom. And because alkenes are higher than alkanes on that list, when we're numbering the parent, we number it from the side that gives the lower priority to the double bond rather than the alkyl group, which is what we were using last time, right? If you'll remember. So that's another one of these things. Well, if we have both now, it's actually the double bonds that sort of take priority. So let's do this. I wonder if I could space these out. I'm gonna try to. Maybe I can even. Or maybe I can. Wonder if I can get them all with like a. Yeah, not all of them. I guess I didn't get all of them. I'm just trying to get them on the next slide so that I can. Yeah, there we go. Let's try that. Just so that we can space them out a little bit. No, that's not it. Okay. All right. Let's give these a try. Okay. Of course. All right. Let's start with the one on the top left, and we'll go from there. I think that's the simplest of these. Okay. Now I'm gonna circle the parent. Circle the parent, and again, it's got to contain the carbon-carbon double bond. This one's pretty simple. Yeah, I mean, in the sense that we would encounter the methyl group from the left or right in the same position, but again, it's not the methyl group that we care about, it's the double bond. Now, notice this is important. There are actually 2 carbons of the alkene, right? All alkenes, are made from 2 carbons, or contain 2 carbons, and so when we're numbering, when we're designating the location of the double bond, it's the first of those 2 numbers that we use to designate the position of the double bond. So if we're numbering this, of course, then it's 1, 2, 3, 4, 5, rather than the alternative from the other direction. And we've still got to deal with our methyl group. Okay, now I haven't even said this yet. Maybe it should have been the first thing I said was, and this is, I'm sure in those rules on the slide, in the last slide, the suffix of the parent changes, right? ANE, this is not a stretch. ANE, right, is what we were using for alkanes, right? ENE is what we now are going to be using for alkenes, ENE, right? And so that's where that comes from anyway, but that's part of the suffix. So the alkene, the fact that this is designated as an alkene is part of the parent. It's the suffix of the parent. So we can still just write 3-methyl out front. And there are 5 carbons, so I'm hoping you're getting a good handle on those prefixes, which indicate how many carbons are in the parent. So 3-methyl. Here, 2 possibilities here. I'm going to write them and then talk about them. So pent, and here's the position of the alkene, 1-ene, or 3-methyl, 1-pentene. Now, both of these, the powers that be, the IUPAC people, say both of them are acceptable. So you can either use that position, and by the way, don't be surprised if you actually see this written 3-methylpentene. If the position of the double bond is terminal, or is it at the 1 position, often that 1 it goes away. Just another synonym for it would not have the 1 at all. But I want us to be extra explicit, meaning I want us to write that position always, and we'll just kind of make that clear up front. We'll always designate the position of that double or triple bond or whatever with a number, even if it's at position number 1. So notice again 2 possibilities. The 1 can go right in front of the ene. Again, it's got to be set off by hyphens there, but it can go right in front of the ene, or it can come in front of the entire parent, and of course it would still refer to the position of the alkene there. Okay. All right, so let's try this. Whoops, sorry, that's not what I wanted. Okay, so let's try this one actually down here on the bottom right. Okay, now one thing that's different, and I'm sure you've recognized this right away, is that this is a cycloalkene in this case, not alkane, but there's a cyclic region to this molecule. So remember, unless we specify otherwise, that cyclic region is the parent. Okay, and so what was I going to do here? I think we're okay. So the parent then would be this. So the question now is, how do I number my parent? Now remember, the alkene takes priority. So I could either, so think about this with me. I could either go 1, 2, 3, and so on, right, and continue around. But remember some of the rules we talked about last time. If and when I can ever give functional groups lower numbers, right, number the parent such that they get lower numbers, I do that. So it would make more sense to go 1, 2, 3, 4, 5, 6, because if I number around this way, the methyl and the ethyl have lower numbers than they would otherwise. So what we can do here is, I'll try to squeeze them in. Yeah, I'll try to squeeze them in down below. This is a cyclohexene, right? Hex 6 carbons. The ENE indicates it's got an alkene in it, and we need to designate that it's at position number 1. So kind of putting this all together. Remember, the substituents are ethyl and methyl. The ethyl in the name comes before methyl, so this becomes 4-ethyl. 2 possibilities here. 3-methyl. 1 cyclohexene. ENE. Okay, or 4-ethyl. 3-methyl. Cyclohex. 1 ene. Again, the location of the alkene functional group can either go right in front of the ene or in front of the entire parent. Make sure we got that. Yeah, okay. Looks good there. Looks okay. Make that a little smaller. Okay, so let's try. All right, so now we encounter a situation. This is just a wrinkle, like a little extra thing that we often encounter. Really, a couple things we got to think about that are different with this one. I'm going to go to the bottom left one here. Okay, so let me get my pointer here to show you a few things. Now, first of all, we've got two alkene functional groups. That's different, right? And so just like before, when we were talking about substituents and having to use our Greek prefixes, di and tri. I'm going to get a little water here. Di and tri and tetra. I've got to do that with the ene as well. And when I do that, again, the IUPAC people say I'm going to actually add a vowel, an A, to the end of the prefix that indicates how many carbons there are. I'll show you that here in just a second when we do this one. So this is going to be a 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. It's going to be a hexadiene. Okay, we'll get to that. But the other thing, okay, is I'm going to show you this alkene is a little different than this alkene in the sense that, remember, this one right here has two things attached to it. It is disubstituted, wink wink. This one is terminal. It is monosubstituted. You don't have to worry about cis-trans with this one, but you absolutely have to think about cis-trans with this one. So here's how this all goes. And I want you to, if you're pondering this, if you're pondering this, think with me while we're doing this, what the what kind of disubstituted alkene this one is. So what kind of stereoisomer it is what I mean. So either cis or trans. I want you to come up with something and think about it for a second. Now, we're gonna number this together. 1, 2, 3, 4, 5, and it wouldn't matter. I'm just gonna put 6 here. If we made the other carbon 6, then that name would be the same. Okay. Now, I'm going to put the cis or the trans, whatever it is. I'm going to do that at the end. So let's put this all together. There's a methyl group at position number 5. Okay, so I'm going to write that 5-methyl. And then the positions of the alkenes, remember, it's the first carbon of the alkene that you encounter. So there's one between 1 and 2, one between 3 and 4. It's really 1 and 3 are the positions. So 5-methyl, 1, 3, hexa, and again, there's that vowel, 1, 2, 3, 4, 5, 6, hexadiene. Or, again, the 1 and the 3 can come before the diene, just like we did in the last examples. Or 5-methyl hexa 1, 3 diene. Okay, and again, if you want to make a note of the fact that we've got that, there's that vowel, right? That A, that hexa. I'm gonna erase this. I just want to point it out. There's that A again that is different when you have multiple of the multiple double bonds. It just, again, the IUPAC people said, and I think they're probably right. It just sounds a little bit better. So it was sort of a rule that they added. Now, one thing we have not accounted for yet is the stereochemistry of the double bond that is disubstituted, and all we have to do to designate that is out front, and there'd be a dash here as well, out front right cis or trans. Now I want to look at this with you. I want to show you that if we're looking at this, remember this one doesn't have cis trans isomerism, this one does. Okay, the two things, and we can get really confused about the fact that there's all sorts of stuff attached. Remember, in our previous simple example, there were just methyl groups attached. But here we've got a whole bunch of other stuff, and you're like, well, does that change anything? Not at all. Look only at the double bond and what's directly attached to it, and look at where they are. So, is all of this stuff out here, because you just consider that a whole group, and all of this stuff out here, if we think about this, so I'm going to do this really quickly, maybe this will be helpful. Think about just sort of longitudinally, drawing a line through that double bond, or again, creating a plane. And I want you to see that this stuff out here and all this stuff out here are both on the same side of that line, right? They are on the same side of that line. So for that reason, these groups are, or this double bond is a cis double bond, okay? And for that reason, again, we go back here, need to write cis out front, okay? So this is a cis double bond. Okay, now let's jump over to this last one. This last one is is even a little bit more complex. Not too much. There actually aren't any substituents. The whole thing is really just the parent, and there aren't any substituents attached, right? And so it has, I'm just going to number it, and I think you'll agree left to right, right? Because we encounter a double bond earlier if we do it this way. Okay, 1, 2, 3, 4, 5, 6, 7, 8 looks okay. Right, the positions of the double bond are position 2 and position 4, right? 2, 3, 4, 5, but 2 the first carbon and 4 the first carbon of the alkene. Okay, so this really becomes, if we're putting this together, it's very much like the last one. We'll get to the cis-trans business here in a second, but let's leave it off for a minute. Let's call this 2, 4. Again, no substituents to write, so we can get directly to it. 2, 4 octadiene. Again, oct with the A, the vowel there, and then there are 2 alkenes, so diene, or octa 2, 4 diene. Okay. Now I want you to think with me. I'm going to get my pointer again, or maybe I'll get my whoops, this, and I'm going to split these alkenes, or just draw a line along them. Again, think about those as being, planes, and I'm gonna do this. Okay, I'll probably erase this stuff at the end, but let's look at this double bond, the one between carbons 2 and 3, and I am going to circle the stuff that is attached. Now again, I know that you're maybe thinking to yourself, well, what this kind of like comes down here, it propagates down here, but remember, where was it first attached and how was it first attached? Think only about the carbons of this alkene and the fact that all of this out here goes that way, right? Whoops, it's pointed that way. So it's on this, all of this technically is on this side, if you want to call it the top of this double bond, and this methyl group down here is on the bottom or the other side of this alkene. So technically, and I'm going to actually do that with the other one, so I'm going to have to erase these here, but technically that makes this a trans double bond. Okay, now let's look at this one, the one between 4 and 5. Well, I'll leave the pen there, and I'm going to now say this, right? Let's look at just the stuff, this alkene, right? This double bond, just the stuff attached to the carbons of the alkene, again, between 4 and 5. Notice how those circles are both on the same side of that line, right? The stuff attached in both cases, all that stuff is, those circles, maybe that's a better way of saying it, those circles are on the same side of that double bond. So this must be a cis arrangement. So for that double bond, we call this a cis double bond. Okay, now I do have to, again, write that into my nomenclature, and because there are double bonds at positions 2 and 4, I also list them in that order. So the double bond at position 2, I'm going to get black here, would be trans, and the double bond at position 4, again, we said was cis, so we write trans, cis, for, again, a diene where both alkenes have, stereochemistry needing to be assigned. Okay, same thing here, trans, cis, again, because 2 was listed before 4, if you want to think about it that way. Trans, cis, octa, 2, 4 diene. Okay. Yeah, so if we're thinking about it, maybe this is more clear. The trans is listed first because the alkene it's corresponding to the alkene that was listed first, right? The one at 2, and the cis corresponded to the one at 4. Okay? You don't have to write those like when you write the name or anything like that, those curved arrows. But I was just kind of trying to clarify. Okay. Yeah, I talked about that. This stuff also we've talked about. Well, not the nomenclature, but the stuff at the top there. Okay, and let's just do our, how are we doing here? Let's just do our nomenclature. I'll try to do a similar thing to what I just did. I'll try to grab these. Well, I'll do it this way. And we'll put them on the next slide. Okay, and we'll put one of them up here. Put the other one over here, whatever, that's fine. Okay, so let's go back. Okay, now the main difference. So basically everything is the same. There's one distinction down here that we have to make, because down here you see a compound with both an alkene and an alkyne. That isn't, that requires us to learn one additional rule. But if you're looking at the one on the top here, top left, the only difference with alkynes and alkenes, simple ones, is that the suffix changes. Again, it's ene with alkenes, it's yne with alkynes. Okay, and again, that would be no surprise if we look at the word alkyne, yne at the ending, and so that's the suffix in this case. Okay, so I'm going to do just what we did. We're just going to go for it here because we have all the tools here. As long as we remember that whole, that yne ending thing rather than ene. And I'm just going to circle. So I just circled the parent. Now, could I have circled this parent? Yeah, sure. In fact, let's just go with this, right? Same name, doesn't matter, because both of those are they're the same size. They both contain the carbons of the alkyne. These are my substituents. And if you look at this one, it's symmetrical. It really doesn't matter if I go. It looks like a lobster. Yeah. It really doesn't matter if I go from left to right, 3, 4, 5, 6, or from right to left. The name, the numbering and the name end up being the same. So, yeah, so let's put this one all together. Now, one thing that's nice about alkynes is they cannot exhibit cis-trans isomerism. Okay, because remember, think about alkynes for a second. All alkynes are like this in the sense that, whatever it is out here, I'll just put R and R, right? It's coming straight off. There aren't multiple things, and so these are always going to be linear, and so so for that reason, you never encounter cis or trans. Okay, so putting this whole thing together again, good chance for you to pause and practice, but I'll just go for it. So it looks like 2 and 5 are the methyl groups. So 2, 5 dimethyl. Hexine, 3 hexine, right? Position of the alkyne, first of, between 3 and 4, but it's the first one we encounter. So 3 hexine. Or, as you might guess, that 3 could come right in front of the ine, like we did before, or just with the alkenes. So 2, 5 dimethyl, hex, 3 ine. Okay. Okay, yeah, that one looks okay. Now, if I'll just put this. I'm looking at the one on the bottom. I mentioned there's something else, so let me just write it. If a compound contains, let's put contains or possesses. This might be on that last slide. I'm not sure. If not, we need to write it. Contains both an alkene and an alkyne functional group, we refer to it, or we name it as an E9. Okay, and you're maybe thinking, I'll just put not ENEYNE. Again, I didn't make this up. This is so not this. E9 with no E there. But again, it sounds like "een" plus "ein" kind of smushed together. So that's really the suffix, and I'll write that. The suffix of the parent is E9. Okay, so putting this all together. Now, a couple interesting things here. Okay, if we go back to our well, maybe I should. Well, let me just go to the functional group priority list and show this to you. Notice how alkenes on the functional group priority list are higher than alkynes. So this clears up any ambiguity that might exist if and when we encounter something like this, because we're thinking to ourselves, maybe, well, shoot, if this was higher in priority, maybe I should number from this side so that got a lower number rather than numbering from this side, right? But again, alkenes are higher than alkynes, and so it leaves no room for guessing here. I'm going to go from right to left because the alkene is higher in priority. So 6, 7, 8. Okay, so that's our numbering scheme. Okay, now we've got our methyl group as well at position number 4. So putting this all together, again, remembering that the suffix is going to be a little different with this one, we end up with not 5 but 4. Did I get that right? 1, 2, 3, yeah. Whoops. 4 methyl. The positions of the "een" and the "ein" respectively, "een" before "ein", are 1, 6, and then octenine, right? Because it's oct meaning 8 carbons in the parent. So it'd be let's make sure I got that right. 4 methyl 1, 6 octenine, or again, same deal as before, 4 methyl oct 1, 6. Yeah. Sorry, I'm just got tripped up here. Methyl oct 1, 6, yeah, E9. Okay, physical properties. One thing that's really nice here is that we don't actually have to say a lot more than we've already said about physical properties of nonpolar compounds, because alkenes are very, very similar. I should say similarly sized alkenes. If we have an alkane and an alkene or an alkyne of similar size, just because the alkene and the alkyne have double bonds doesn't make them polar molecules. Now, there's a little bit of an increased polarity there, and it's partly just because of stuff that if you took 1A, you talked about valence bond theory and molecular orbital theory, and how pi bonds, or electrons in double and triple bonds, kind of are localized above and below what we call the internuclear axis, the axis that separates the two atoms that are bonded together. And because they're a little farther away, they're a little less tightly held, and that electron cloud can kind of move around and create a little bit of an additional dipole. But that's nothing profound. Okay, and so for us, don't worry about any of that. For us, we will say that alkenes and alkynes of similar size to a particular alkane will act very similar from a physical property standpoint when we think about things like solubility and melting point and boiling point. So again, that's a really nice thing. Nonpolar molecules, and you see this mentioned on the slide, right? The only operative intermolecular interaction is the dispersion forces, which is a weak one as compared to the others, right? So in a relative sense, these types of compounds have low boiling points, low melting points, low solubilities. Remember, like dissolves like, right? So nonpolar things don't really usually dissolve very well in polar solvents like water, right? So they don't have very high water solubilities. Sorry, there's a mower driving by here. So anyway, this is kind of a cool experiment. Again, if we do this in the year-long course in the lab portion of the course. If you think about orange peels, citrus peels, they have a bunch of this compound, limonene, in them. Limonene is actually a terpene if you think about it. Going back to what we first talked about, if you think about circling this piece and I guess this piece, there are two isoprene units. Anyway, it's nonpolar, even though there are double bonds, right? It's only made of carbon and hydrogen, and it's very, very insoluble in water. In fact, what's cool is you can do something called a steam distillation, where you grind up a bunch of orange peel, you put it in a round bottom flask like this. This is a distillation apparatus. You put it in a round bottom flask like this, and with a bunch of water, actually, you heat it up, and water vapor comes out, but it also sort of carries with it this limonene, which is really an essential oil. I don't know if you've heard of essential oils before, but it's a real oily compound. And because it's so non-polar, it actually, in this, if you think about what you're distilling off, it's kind of cool. You end up with two layers, and you can actually just pipette off the limonene, and it smells really nice. In fact, some like if you ever go, sometimes folks, and I understand this, I don't blame them, they don't want to use, like, let's say you have an ant infestation, or in your kitchen, right? And you don't necessarily want to, maybe you want to spray Raid outside, but you don't necessarily want to spray your whole kitchen with Raid or something that's a little harsher. And so there are these not only cleaners, but also insecticides that are more natural, and a lot of bugs really don't like limonene, and there are some other oils and things like that they're kind of put off by. So you can use it that way too. It's kind of fun. It's really fun to do steam distillations like this one. End up with essential oils. They smell nice, and they have other uses. So kind of cool. And of course, and that kind of plays into this idea that these nonpolar compounds are again, they don't pack together real tightly because again of those weak intermolecular interactions, so they have low densities. And so it's really the limonene, I think I mentioned this, the water that's coming off is on the bottom, the limonene just floats on top, and you can pipette it right off the top, again because these types of compounds have relatively low densities. So it's kind of a fun experiment. All right, what's next here? All right, looks like, okay, so as we mentioned last time, very often we end the chapter or give a part of a chapter is given to the discussion of, one or a few different types of reactions that are encountered for a particular functional group, right? Or in this case, alkenes and alkynes. Have characteristic reactivity, and they undergo similar types of reactions to one another. And so we look at a few of those in this chapter, and these are called alkene addition reactions. Now, a quick note on mechanisms, and I've done this multiple ways, and so I think what we're going to do this semester, okay, is, and I've done this in other semesters as well, so it's not like we're this is totally abnormal, but all right, so in organic chemistry, one of the most challenging components, if you're really kind of digging deep, is reaction mechanisms. And a reaction mechanism kind of depicts the flow of electrons in a chemical reaction. And we use these curved arrows to kind of show that. Now, what you will notice is Bettelheim does write a few mechanisms from time to time. And there's a tremendous amount of explanatory power there, but it also is kind of a disservice if you don't really write a lot of them and really dig into it, because you kind of are left wondering. There's just so much detail there, okay? And we couldn't, unless we really dealt with mechanisms at a deep level, and we don't quite even have all the tools to do that at this point. They can actually, in some cases, be more harmful than good. So what I want to do is I want to say this for now. We will not be writing mechanisms for these reactions, or probably any of the reactions that we come across. Probably, okay, and if we do, I will kind of give you all that you need to know for a particular reaction and its mechanism. Okay, well, we would explain all that we needed to explain, but for now, you see some stuff about mechanisms here. It's good to it's really this is really interesting stuff. So what you're seeing here is a curved arrow where a pi bond or a double bond is broken, and that pair of electrons forms a new single bond from one of these carbons to that hydrogen. And in this case, what you're seeing is this bond breaks. Both of these electrons, again, that's what the tail of the arrow represents, are being transferred to bromine to make it bromide. Okay, so one of these carbons then gets a new hydrogen, a new bond to hydrogen is formed, but the other one, if you think about it now, is deficient. This is called a carbocation. Okay, and Bettelheim might talk about carbocations and carbocation stability, and in this case, right, bromide now uses a pair of its electrons to form a new bond. There's a negative positive interaction with carbon, and of course the bromine goes there. And I was just going to finish that thought. Bettelheim might talk about carbocations and carbocation stability, and later on we will too, but for right now we're going to leave mechanisms alone. Okay, so we won't be writing them at this point. Okay, there's plenty of other stuff to do and plenty of other challenging topics with atom. And in fact, if you look on this slide, notice I've left the option open for us. Write the mechanism for the addition of HCl to propene. We're not going to do that. Okay, we could, but we're not. Okay. So what I want to do is actually, did I have a blank slide? Before we do this hydrohalogenation, what I want to do is I'm gonna exit or get out of this, and I'm gonna actually add one more slide up here because I want to just generally for a second talk about, this is what I want to do. I want to just talk generally about alkene addition reactions, what they are, sort of what we're getting ourselves into here. Okay, let me change color here. So let's say this, alkene addition reactions, because all of the reactions, this is not all of the reactions that alkenes do, but in this chapter, those are the ones that are highlighted here. Okay, so let's say we have an alkene, and the ones we talk about sort of follow this form, and we have like A, B, this is generic, right? We don't care what's there. Okay, so alkene addition reactions all have, this in common. Okay, if we take a reagent, and typically that's like, I'll just put, no, it doesn't have to be this. Let's just make it generic too. XY, okay, and then I should have left myself more room than that. I'll go down this way. That's my reaction arrow. So let's write this. Alkene addition reactions occur. Maybe I should make it singular. Yeah, let's make it singular. An alkene addition reaction occurs when a reagent, in this case we're calling XY our reagent, is added across, you'll see what I mean by that in a second, the carbons of the alkene or the double bond. So what we mean by that is, so what we mean by that is, X goes to one carbon of the alkene. Well, it ceases to become an alkene when we're done here, and Y goes to the other. Okay. Now, one other thing to point out, and you'll see this, the double bond breaks, and essentially one of the bonds of the alkene breaks, and two new single bonds form. Actually, let me say this. Let's say this. Actually, this will be nice to depict graphically. And it doesn't really matter which one we pick. Actually, I didn't mean to. Let's do it like that. It doesn't matter which one. So let's say this. One, and I've shown it up there. So one of the bonds of the alkene breaks. Okay, and the XY bond also breaks. 2 new single bonds are formed. Okay, so what we end up with here, and I'll go like this because we're running out of room there, is this situation. So still one single bond between those carbons, still A, B, C, D are there, but now we have X over here and Y over here. Okay, so 2 new single bonds form, right? And we can actually write those in red since we cut the other ones in red. So there's our new single bonds. 2, again, the carbons of the original alkene. So that's just sort of generically what an alkene addition reaction is, and it's helpful, you know, because now we're looking at a specific one. We call this hydrohalogenation, you know, I think it'll be clear what's going on, and I can color code this as well. Now, I'm going to come back to this information again. I want to kind of say a few things, you know, in more of a general way first, and then we'll go back and look at that example. So, well, let's say this also. I forgot to put this. I wanted to put this on this slide. It's on that next slide also, but I would add right here these obey. I'm running out of room here, and they obey these types of reactions. Obey Markovnikov's rule. Maybe I'll these reactions obey Markovnikov's rule. Okay. Now, Markovnikov's rule, there's different ways of stating it depending upon if you're talking about a carbocation or not, which I mentioned in that last slide. We're not doing right now. We're not writing mechanisms, and we will encounter carbocations later, but we're going to leave them alone for now. We can get by with saying, you know, in this case with hydrohalogenation, the hydrogen goes to the less substituted carbon. The halogen goes to the more substituted carbon. You're like, what does that even mean? So let's, again, a little bit more groundwork here. Let's say something like you know, carbon substitution. What does that mean? Or yeah, let's just say that. Substitution of an atom in this context. That'd be better. Come on. For example, a carbon atom. Sorry. Example. Okay. So, all right. So here's what we mean by that. The more alkyl let me just write it. The more alkyl, we know what those are, right? Substituents a carbon has, or an atom has, the more substituted it is. Okay, and we'll encounter this, you know, quite a few times in our course. But let's say, and so let's bring this back into context, and we'll get to this here in a second. Hydrohalogenation. And there's an example on the last slide I'll refer you to, but I'll just put this is addition of HX. And okay, think about this for a second. I'm going to write H dash X, where X is a halogen. That's where this comes from. Cl, Br, or I, typically, across an alkene. Again, what that means is across the carbons of an alkene, H goes to one carbon, X goes to the other carbon. Now, where Markovnikov's rule comes into play, and let's look at this example here, okay? I'm going to get the laser pointer out. And then we'll do another example kind of to try to drive this home. Look at propene for a second, okay? Well, I guess we could do yeah, let's just look at this one, and I won't sully it up. I was going to draw on it, but if we're looking at the carbons of the alkene, notice, and let me just do this for a second. This is always helpful for me. I don't know if you're getting comfortable with line angle or bond line, but this is propene, and to me it's actually even more clear if we look at the bond line version, because if you're thinking about, there's two carbons of the alkene, right? There they are, same thing here and here, right? So if you're looking at the carbons of the alkene, this carbon on the left, right, is, I'm going to write more substituted. Come on now. Right? And this one's less substituted. Okay? Because, think about this with me for a second. Let me get back to the pointer. This carbon is attached to, so it's how many other carbons it's attached to. I know I wrote alkyl groups, but just think alkyl groups, right? The first point of attachment is carbon. So this carbon is attached to two other carbons. This carbon is just attached to the other carbon of the alkene, right? No other alkyl substituents attached. For that reason, this is the more substituted carbon, and when HX, notice it's HCl here, it's more specific, right? But X could be, again, we're talking about HX, HCl, HBr, HI. X could be either of these halogens, right? Chlorine, bromine, or iodine. Think about this as XY, right? Here's our XY here, X dash Y in our generic example. But it's more specific, right? And so one of the H is going one place and the chlorine's going to the other, but if it's not a perfectly symmetrical alkene, it actually matters where they go, because we create two different compounds if we, depending upon which way, the X goes or the H goes and which way the chlorine goes, okay, which carbon they attach to. So Markovnikov's rule, and you see it stated here, is that the hydrogen goes to the less substituted carbon, the halogen itself goes to the more substituted carbon. And that's what you see here. Okay, and we'll practice this and another example of this, but I want shoot, I was gonna, same thing, right? More substituted, same thing here, right? More substituted, and of course less. There you go. So if you follow this through with the pointer, notice how the hydrogen ends up attached to this carbon, right? And notice how we've done it both ways, and the names are listed, okay, which is fine. We're not focused on the IUPAC names here. We're focused on the two possible structures that could form, and the fact that one of them doesn't and the other one does. Again, according to Markovnikov's rule, that hydrogen goes to this carbon, which is exactly what you see here. That hydrogen goes to this carbon, right? And then the leftover thing, the chlorine in this case, it would be chloride. It becomes chlorine when it's attached. Is attached to then what was originally the more substituted carbon. Okay, so let's do an example of this. Another example, I should say. Okay, let's do and I'll do bond line in case that's something that you're becoming comfortable with, and hopefully that's true. Hopefully you are. So let's do, I don't know, let's do something like this. Hopefully that goes away here in a second. There. Yeah, that's well, let's do something like that, okay? Plus, let's do HBr. And here's a great opportunity, again, for you to pause the video, see what you come up with, okay? Because there's a couple questions we have to answer for ourselves. I'm just going to continue ahead, right? Here's my alkene, right? And I've got two carbons, right? Which one, the question to you would be, which one of those carbons is more substituted? And then can I apply Markovnikov's rule, okay? And I'm going to go ahead and write, this one is more substituted, okay? This one is less substituted, okay? Because again, this carbon has 1, 2, 3 other carbons. This carbon has, and if you don't count the carbons of the alkene, you would say there's two alkyl substituents. This one only has one alkyl substituent. Or you could think about it like, this carbon is attached to two other carbons. This one's attached to 1, 2, 3 other carbons. Either way you slice it, the one on the left is more substituted. So if we then break that pi bond, draw everything else, and then go ahead and add, and it doesn't really matter, we'll deal with stereochemistry later, but I'm going to go ahead and in red, I'm going to add the H and the Br, but the question again is, where do they go, right? Because we've got two options. We've got this option where H goes here and Br goes here, or we've got this option. Let me just draw them both. We won't do this for all of them, but we've got this option where where H goes here and Br goes here. And again, what did Markovnikov's rule say? It says H goes to the less substituted carbon, which means this is appropriate, this is not the way it works, right? Okay. And don't be surprised, like if you're looking at your homework problems and you see, you'll see this written just kind of like, total bond line. Whoops. I haven't left myself a lot of room here. You'll see it written like that, and you're like, well, they look a little different, right? But remember, the bromine can be pointed. We're not worried about stereochemistry right now, so we haven't used dashed and wedge bonds, so we can really put that bromine anywhere. And then remember, the H here is implied. This H is often implied, and there is even another H there, right? This is a CH2, so don't be surprised if you see that as well. The sort of more bare bones line angle formula there. Okay. All right. So hydration is next. And I didn't point this out, but the name kind of gives away what's going on. Hydrohalogenation. So the idea is we're adding, and if this is good for flashcards, what's a hydrohalogenation, and then maybe on the back, you could do an example kind of like we're doing. But hydrogen, right? Halogenation, halogen, the addition of a hydrogen and a halogen. Now, if you think about hydration, it's the hydrated, right? Or hydrating or hydration, right? Any of those words make us think water. Now, there's a couple things here. Some of these alkene addition reactions require catalysts. And I'm going, again, this is good information for flashcards. I'm going to point out if and when a catalyst is used, and you need to know that. Meaning, if you encounter, a question like this on an exam, and I ask you about a catalyst, or I ask you a common thing that we do, and we practice this with our homework as well, is if I wanted to make this, what are all the things I would need to add together to make it? So we would, of course, need our alkene, right? If we're talking about these types of reactions, alkene addition reactions, I'd need my alkene, I'd need my other reagent, whatever that is, my XY, right, generically my XY, or my hydrohalogen, if it were the last, my HX, if it were the last example. And then in some cases I need a catalyst. Now with hydrohalogenation I don't. With hydration I do. And typically, so this is what we call an acid catalyst. We also sometimes call it a Bronsted-Lowry acid catalyst. I'll just call it an acid catalyst. And I want you to know, this one needs one, and this one usually employs sulfuric acid. Now, I suppose there are other possibilities, but for us, we're just gonna always use sulfuric acid for hydration, and that typically is the one that's used. So, so let me go. Good, I have a slide there. We can come back to these in a second, talk through them, but let's do a similar thing. Let's do. Whoops. Here's hydration. So I'm just going to write addition of water. Now, I always think it's helpful. So, of course, requires acid catalyst. And very little of this. You just need a little. It's like 5 mol%. You don't need to know what that means, but like, you could imagine maybe what 5 mol% means. Just a little is what I'm getting at, though. Acid catalyst. Now, when I say addition of water, I often like to draw it like this. I always think it's so helpful because again, we're back to our XY, right? Because to me, then I know Markovnikov's rule. It actually still applies. If you look at the last slide, it applies in this context as well. And you'll see what I mean here in just a second. Let's do like yeah, let's do like this. Okay. Yeah. Kind of just again, we're just trying to make I'm gonna make myself a little extra room there. We could even do that. Just kind of look, something that looks different, kind of obscure, right? To practice with. Okay. Now again, here's our water. I'm gonna write it HOH. Nothing wrong with that, right? Water is H bonded to, you know, I could also write it like this, right? H-O-H. That's fine too. But I like, the reason I group it like this, H-OH, is because I want to be thinking XY, and I want to be thinking, I'm going to write my H2SO4 here. Often we put it over the reaction arrow. There's my catalyst, right? Sorry, I should have said catalyst. For some reason I didn't put the T there. There it is right there. Now, think with me. Think through this with me. Okay? So if I go back to my alkene, right, I have my H and my other piece, my OH. Markovnikov's rule, remember, says the hydrogen adds to the less substituted carbon of the alkene. The other piece adds to the more substituted carbon. So can we agree, right, that the carbon on the left is what? Less or more substituted? I'm going to say less. Okay, this one's more substituted. And once we've figured that out for ourselves, we've made it a lot easier. Okay, I'm going to break the carbon of the alkene. I'll put everything else there. And then remember, I'll use some highlighted bonds there. And again, it doesn't matter where we put these necessarily. I'll just put them here and here. Maybe we'll put it here and here. Yeah, how about that? That's fine. As long as they're on adjacent carbons of the alkene, the way we're writing it now, I'm going to go ahead and put my H here, less substituted carbon, right, and my OH, the other piece, there. Okay, again, don't be surprised if you see this written something like this. And you're like, where'd the H go? But again, this is line angle, right? It's bond line or line angle. And so very often once we redraw the line angle formula or whatever, we may choose not to draw that hydrogen. Again, don't be surprised if you see it like this, like the one on top too, where the H is explicitly stated, just because that's kind of what we're doing here, right? We're showing it like where each piece goes. So, okay, I'm gonna get some water here. Okay. Now, if we go back, I said we would go back and look at those other ones. We can do that as well. Just quickly, we need to continue to move on. But if you look at substitution patterns here, right? Less substituted carbon, more substituted carbon. So if you come over here, notice, right? The H ends up here. There it is right there, right? And the OH, the other piece of the water, ends up on this carbon. Okay. Same thing down here. Not same thing, but same idea. More substituted carbon, less substituted carbon. So again, the H goes on the less substituted one. The OH one goes on the the OH goes on the more substituted one. And we will not worry about mechanisms right now. Okay. All right. So addition of chlorine and bromine, iodine and fluorine, for reasons we won't go into, are less useful in this context. And again, there are reasons, we just won't discuss them. But this is called halogenation. So we have so far we have hydrohalogenation, we have hydration, and we have halogenation, right? And the only word you see in halogenation is halogen, right? And so you were thinking, oh, okay, now we're adding just the halogen. Now, it's two of them put together, because remember, these are, right, do you remember Brinkelhoff? B-R-I, and I don't know how you learned this. I learned it Brinkelhoff. These are all the diatomic elements, right? Or actually, I've different ways, but another one that was just actually I learned not too long ago. A student actually taught it to me. Horses need oats for clear brown eyes, like just I, not EYES, but I. And it's just an acronym for all of these elements that are actually diatomic, right? So when we say chlorine, we really mean Cl2, same thing with bromine, iodine, fluorine, or others too. But in this case, again, we're just thinking about chlorine and bromine, okay? So halogenation, generally speaking, looks like this, right? We have an alkene. Let's just make something. Well, do our little intro here. Halogenation, right? Addition of a halogen, diatomic of a diet. Maybe I'll put diatomic across an alkene, such that we have an alkene here, and let's do something like that. Plus, actually, let's do something like that. Again, just there's something that we can point out here. Plus, we'll do Br2. But when we draw it, again, it's always helpful to kind of show it as it exists with that single bond there. Okay. Sorry. I was thinking about that. Sorry. Got distracted there. So, but here's another thing I want to point out. There's no catalyst necessary, and if there was, we would write it either over the, usually over the reaction arrow, okay, or put it somewhere and highlight it as an important component. So, halogenation, no catalyst required, okay, and in this case, again, that double bond breaks. I'll try to put everything where it goes, but the question double bond breaks, or single bond left. The question we should be asking ourselves, especially after those last examples, is this like do I have to worry about Markovnikov's rule? So Markovnikov's rule, right? If we put question mark, I'm just going to write NA, not applicable, right? Why is it not applicable here? Well, think about it with me for a second. I'm taking, right? Two things that are what? The same, right? They're exactly the same. So, it doesn't matter how I slice it. I put this bromine on this carbon and this bromine on that carbon, or vice versa. I'm doing the same thing, right? So, nothing. That's not, I don't think, too difficult for us to kind of recognize or see. So I'm going to put, one of them here, right, and one of them there. Well, let's just put it. That doesn't really. Again, it doesn't matter. Put it there, and we'll put our bromines in those places. We'll put our bromines here. Yeah, so it looks good. Again, different ways of writing this. You can imagine other kind of just ways things are arranged, but structurally it has to be like this. I mean, I don't mean like different constitutional isomers. I mean, it has to be like this. The bromines have to be on those particular carbons in this case. Okay. Now there's kind of a cool. I'm trying to remember if I have this linked. I think I did. I do or did. Maybe I don't. Oh yeah, okay. See if I got it. And I'll let you watch this on your own. This isn't like I don't think it's an earth-shattering thing. In fact, I don't even know if there's sound. But I'll let you watch that on your own. But this is what we're getting at here is this is kind of a cool thing that you can actually see this reaction happening, because if you think about cyclohexene, this here, and this is true of lots of alkenes, but in this case, this is colorless, okay, and this is actually colorless, but this is like a brownish reddish, okay, and so what happens is you throw these two things together, the ene, the alkene, and the bromine, and right away, of course, the solution changes color. I'll just put reddish. Down here it's saying a deep red color. Is reddish 2? I don't know. Let's call it brownish red. 2 Ds. Good question. Some of you know the answer to that. I don't. I don't even know if reddish is a word, but The whole point, though, is qualitatively. What's a qualitative observation, right? A quantitative one is like numbers that we derive from something, right? Whether it's some measuring device or a balance or a scale or whatever. But qualitative observations are where you're describing the qualities of things. And in this case, qualitative observation would be we go from a brownish, reddish solution to one that's colorless, and that tells us really that all the bromine's gone. It's reacted away. So that's kind of one thing. You can actually see that happening. Okay, I'm just seeing how much we have left here. Okay, now our last, in this chapter, at least for what Bettelheim brings up, our last alkene addition reaction that we're going to discuss is, we'll just put hydrogenation. Okay, that one's addition, like the name, addition, like the name suggests. What's going on here? Of hydrogen. Again, maybe I should have put diatomic because it's one of those same Brinkelhoff elements. Diatomic hydrogen across an alkene, right? The carbons of an alkene. Addition of diatomic hydrogen across an alkene. Okay, so the way this works, and again, this is a nice one. We can go back to, we looked at this one earlier, right? We can, I'm going to put H2 there, but again, we're always looking for that XY kind of notation, because it reminds us that we have two pieces. The reagent has two pieces that coded to both of the two different carbons of the alkene. Now you're thinking to yourself, I'm hoping at least you're thinking to yourself, okay, I don't need to worry about, like last example, I don't need to worry about Markovnikov's rule because the pieces that I'm adding across the alkene are the same. Now, in this case, though, a catalyst is required. So I'll write that, catalyst. And I'm just going to put a TM, if you want to add, sorry, I didn't have room there. TM in this case, I mean to refer to as a transition metal catalyst. So, for example, the ones that are common are palladium, platinum, or nickel. Nickel's probably the most popular because palladium and platinum, you might know this, are both very expensive. Nickel's not very expensive. So let's do this. Again, one of the carbons of the alkene goes away, and the HX bond, breaks. Maybe I could be doing this each time too. Should I be doing that each time? Right, this is breaking. One of these is breaking. I don't know if that's even helpful. Going back and anyway, you get the idea. Now I'm obsessed with going back and did I do it on all of them? Come on. No, I didn't. Sorry, tangent there. So let's go back to here. Right, two new bonds form, and here they are. Right? Or again, we can put this one up here, kind of like we've been doing. Let's put our H's on, and our H's on. And again, don't be surprised if all you see as an answer here in the answer key, or in the back of the book, or even on a quiz or on an exam, is the bond line structure. Because those hydrogens, again, even the ones we added, would then be implied, right? All right. Now this is a really cool reaction, actually. Again, if we were to talk about the mechanism of this reaction, there's what we call an adsorption that takes place, where the alkene actually attaches to the surface of the transition metal. Just the purpose of the transition metal. And so, by the way, you don't need all of them, but don't be surprised. Just all we need is one. In fact, let me just write nickel here, right? You don't need all three. You just need one of them. So we need to actually put one of them over the reaction arrow if we draw a reaction. Or again, if we're asked the question, what would I need in order to make this product? Because we do that a lot. Okay, what are the things I need to make a product? Or given this product, what was it made from, right? I guess that's the same thing. I just said the same thing in two different ways. Or, right, if I'm given all the reagents, what would the product be? I guess that's the other possibility. But I'm losing track of where I was at. Oh yeah, we were talking about the surface of these transition metals and how really the alkene comes and sets down, really bonds in some sense with the surface of the metal. Same thing happens with the reagent, and then it kind of provides a place for them to come and meet up. A lot of details there we're leaving out, and again, we're just not discussing the mechanistic piece here, okay? All right, we're getting close here. The very last thing, some of this is actually review from 3A or 1A. The very last thing I want to go into is like energetics of alkene addition, or really a reaction in general. But these are mostly exothermic reactions, and so I want to remind you, or I want us to remind ourselves what an energy diagram looks like. So energy diagram for, let's put exothermic reaction, and we'll do one for an endothermic reaction as well. Okay, in fact, let me just make sure I leave myself enough room to do that. Okay, so these energy and by the way, alkene additions, most of them, I think this is probably on the last slide, reactions are mostly exothermic. And I'm hoping you remember, I'm sure you very likely remember, what that word means, or at least having heard it. It means energy is released in these reactions. Okay, now often we show that with, again, what we call an energy diagram. So we'll actually put energy here on this axis. Sometimes we'll actually write, or enthalpy. You may remember that word. Enthalpy just means really heat energy, heat absorbed or released at constant pressure, but usually we just think about it as heat released or absorbed in a reaction. Now, if you think about what these reaction profiles look like, it's often something like this. Now, we normally say reactant or reactants here, sort of generically, and product or products here. Okay? So if we're thinking about an alkene addition reaction, we have like our alkene here plus whatever, plus our XY here, right? And then our product or products is like this. Oh, no, not a double bond. It's like this, where we have X and Y over here. Okay. Now, couple things, okay? This hump, if you're thinking about, again, the energy axis here, or enthalpy, I'm going to actually get a different color. Let's go with blue. Okay, this amount of energy, you may remember this hump, okay, from where you start out to right here, is referred to as, I'll just put E sub A. Well, I need that. I'll write it over here. E sub A. Which is activation energy. We call this the activation energy of the reaction. Okay, and I want you to be able to kind of decode this, or like if you're given an energy diagram, be able to sort of know all of the different pieces of the diagram, be able to determine if this is a diagram for an endothermic or an exothermic reaction. We've already said which one it is. But yeah, so I'm already drawing down here, right? So this is the difference in energy or enthalpy between products and reactants. Sometimes we call this delta H. And it's really the delta H that tells us whether the reaction is endothermic or exothermic. So I'll just put this equals enthalpy change. Or if you're talking about just potential energy on this axis, on the y-axis, we could just call it energy change, but normally we call it delta H or enthalpy change. And in this case, if you think about this with me, okay? Laser pointer, right? My reactants have more energy or enthalpy than my products, which means there must have been, along the way, a release of enthalpy, right, or energy, of heat energy or just if we're thinking about potential energy. So either way, we're saying a release of energy. So in this case, the enthalpy change is, I'll just put negative in this reaction. Now we haven't actually written numbers over here, so we're not going to come up with a number, but negative enthalpy changes refer to what we call exothermic reactions, right? So energy slash heat was, and you guys know this, or you've learned it before, okay, we're hoping to remember it, was released in this reaction. Okay, now the other thing that I like to point out here, this is what's referred, the very top of this hump here is referred to as a transition state. Okay, and if we're thinking about collision theory, a lot of this comes into play when we first in 3A or 1A start to talk about collision theory. So two reactants coming together and hitting one another, and remember, they have to hit each other, two things really, with the correct orientation and with the correct what? Energy. That's where activation energy comes into play. If they do, if those things are both true and correct, then we reach the transition state sort of collection of atoms, and then that collection of atoms can be proceed to product. So really what I normally say here is, highest energy collection of atoms that a reaction like proceeds through, maybe, or that forms in going from reactant to product. Let's say it like that. Okay. All right. And normally down here, I should have done this right away. Normally down here on this axis we put a number of different things. You could put time, but a lot of times we'll just make it sort of generalized. We'll just put RxN means reaction. If you see me do that, or if you've seen me do it before, maybe I didn't specify. RxN is just shorthand for reaction progress. So progress of the reaction in this case. Now, one other thing I want to highlight here. Let me just get a different color to do it. And again, you've encountered this before, I know, but remember, since we've talked about catalysts in this chapter, let's not forget to remind ourselves what on an energy diagram a catalyst would be doing, right? Or depicting the fact that a catalyst, remember, it does not change the relative energies of the reactants or products, and it certainly doesn't change their identities. Absolutely not. But remember, I'll just put reaction pathway for catalyzed reaction, the one with the catalyst. Okay, I'll just put low. Remember, I'm running out of room here. Catalysts lower activation energy. And, okay, sorry, and in so doing, and for this reason, maybe I'll just put for this reason, and this is probably the stuff that's intuitive to us. Catalysts do what? They speed up reactions. They increase the rate of reaction. And for this reason, they speed up the progress of the reaction, or speed up the reaction, i.e. increase its rate. Okay, so I don't want to. I want to show you what the and again, that stuff. A lot of that is review stuff. It may have been a while though, so it's good for us to remember those things. So if we're talking about an energy diagram for an endothermic reaction, I'm not going to go write all the same things on the slide, but the main difference is, you might start down here, and again, it's sort of arbitrary where we're starting, but the thing that's not arbitrary is that we still have reactants over here and products over here, But notice, right, if I get my blue, main difference here, I won't write all the other things. This thing we need to write, though. You still have an activation energy for sure, but notice the main difference here is delta H, right, which is the enthalpy change, is positive for an in this reaction. Okay, all those other things again would we could diagram them here, but that's the main one. So enthalpy, reaction progress, and all that other stuff. Main thing here, though, is this is an energy diagram for an endothermic reaction, right? So this is a reaction in which, just so that we don't leave it hanging, endothermic reaction, energy / heat was absorbed during the process of this. It was absorbed, not released. Okay, during the this process, this reaction. Okay. Okay. Let's stop there. Okay, for chapter 3.